let's look at some ways at navigating global arrays. This also applies to local arrays, but it's probably more likely to be done with global arrays. First of all, up here I have two windows, by the way. Let me make sure this one is always on top. One we can look at the code, and the other one we can execute in. All right, so this is the code here. I'm in VI, and we initially set up a three-dimensional matrix or a three-level tree, whichever way you want to look at it. I kill all previous instances of the global array A. Then I go from 1 to 3. I set up arrow A sub I equal to I. So at the first level, I'm putting something there. At the second level, for J goes from 1 by 1 to 2. I kept it small because we don't want huge arrays here. It gets too much printout. From 1 to 2, I set up arrow A sub I comma J equal to I, concatenate the string with an asterisk in it, concatenate J. So when we print it out, we'll know it's authentic. We'll know it actually came from the place we think it came from. And then finally, you notice I'm going deeper in blocks here. I go from K goes from 1 by 1 to 2, and I set up arrow A sub I comma J comma K equal, again, it's pretty much the same thing. I concatenated with a string with an asterisk, concatenated with J with an asterisk with K. So that'll be stored at the third level. So this tree it's three-dimensional, and it's fully populated. At each node in each node at each level, there's data stored. If I'd only stored it at the lowest levels, up arrow A sub I, where I goes from 1 to 3, and up arrow A sub I comma J, where J goes from 1 to 2, they would have no data. They would exist, but they would show up if you did a $sign data as existing, but having descendants, but not having any stored data. All right, first of all, let's try running them through, and I'll run the program right over here. And there it is. I'll scroll back to the starting point here. Starting point was right there, this test 1. First of all, we're going to print it out using a more traditional way of printing it. We know what the structure of the tree is. We can just go ahead and print it. So initially we set I equal to the empty string, and now we have a for loop. Notice the two blanks. It's forever until we, of course, hit the quit. Set I equal to $order of up arrow A sub I. Now what that's going to do is return the next ascendant value of the variable I, the only subscript in this case. We start off with the empty string, which means the first time through here, I will come back with the first value, the alphabetically first value of the first index. If we come back with the empty string, if I comes back with the empty string, we quit. Who does that quit apply to? It applies to that 4. The quit applies to the 4. So if we get the empty string, we're going to quit the loop and we'll move on to the next test. Notice after the quit, there's also two blanks because quit doesn't take an argument. Not in this case anyway. It can, but not here. We put two blanks after it. That's required. Then we have the do. The do invokes the first block. The first block is, of course, the one with one dot in it. You have to get these dots correctly. If you don't, you can make a mess of things. So what I do first of all is I write out I, which is the value of the index, and my little string of equal sign to greater than sign, and the value stored at the index, which should be the same thing. So there it is right there. There you see the first output I contains a 1. Excuse me, the first index 1 contains A sub 1 contains 1. All right, so now we move down to the next level. The next level we set a J equal to the empty string, and we do basically the same thing, another for loop, where we will get values of J, successive values of J, beginning with the first one. Order always gives you the next descendant value of the last index you give it. So if you've given it 2 indices, it's going to give you the next descendant value of the second index, in this case J. Again, if J comes back empty, it means we're done and we quit. Again, notice the two blanks and the two blanks here. The quit applies to the 4. Now when we run out of, at this level, we would of course cycle back to the upper one. When it runs out, we finally exit everything. Okay, the next line here is we've tabbed in 5 positions. That's a tab of 5. We write out J, which is the value of the index, and then we write out the value stored at up arrow A sub I comma J, and you see it there. The first one to come out is I which is of 1 star 1, which is what we expect. Okay, now we are going, whoops, I hit the down key on the wrong window. All right, now we're going to go down to the third level. K is equal to empty. This is really the same code. Now you notice we're two blocks in, and now we will go to a third block. Again, 2 blanks. We get the next value of K from the $ order. And when we run out of K, we'll quit the for, which will take us to the outer loop, which is the J loop. And we quit the J loop, we go to the I loop. The I loop may or may not restart everything at that point. And then finally down here, we indent 10 positions. That goes to position number 10. We write out K, and then we write out the value of up arrow I, comma J, comma K, which the first time through over here is 1 star 1 star 1. And we continue until we've done the entire matrix. So you see over here in the output, there's the first level, 1, 2, 3. And then at the second level, we have 1 and 2. At the third level, we also have 1 and 2. And we traverse the entire tree and or matrix, whichever you want to see it. And we list out the values that were stored, being mindful that these values are stored at the appropriate nodes. This tree is fully populated. Are there other ways of doing this? Yes, there's almost always other ways of doing it. First of all, I've got 2 parts here. One to make it a little bit clearer, I hope. Let me scroll down a bit here to get the 2A up to the top. In a MUMPS database, conceptually, and in many cases in reality, you'll have to ask the database provider how they do it, but the global array keys in the indices are stored alphabetically, as though you just took the name of the global array and the values of the keys and kind of concatenated them together with something in between. In my case, I use a byte with a 0001 in it, with nothing but all zeros and a 1, the actual binary value 1. That has an effect on keeping things alphabetically correct. But anyway, they're stored in order. This is because we've got things like order and data and so forth. We need to be able to do that. So what you're seeing listed over here, well, first of all, let's see what we're trying to do. We set x equal to the string up arrow A, and then we forever, again the 2 blanks, set x equal to $query of @x. What $query does is it returns you the next thing in the database, the next key in the database, which if I give it up arrow A, it would give me the very first value, the very first key of the global array A that has indices. Up arrow A has none, but it would see the very first one. The very first one that has indices is, of course, up arrow A with an index of 1. And there you see it up there. That's the first thing that got printed out. Again, we check to see, because $query gives us an empty string when we run out, again, the 2 blanks at the end. Otherwise, we write out the value of x. And there you can see the value of x, which is the first key in the database. Now, $query inserts quotes around the indices. This is fine. You can put quotes around numbers or not. You don't need to put quotes around numbers, but you need to put quotes around everything else. So by default, it's going to put quotes. But there it is. The next one in the database, then it just cycles on. The next one over here you can see is 1, 1. And the next one is 1, 1, 1. And the next one is 1, 1, 2. You see it's alphabetizing. Now the next one is 1, 2. And so this is the actual order of the keys in the database for this tree. $query gives it to you. Notice you've got the @x when you're talking with $query, not just passing x. If you're passing x, you'd be passing the value of x. Instead, we're passing the global array reference x, so it knows what to do with it. It's a little irregular, but it works. So there they are. The other cycle here, 2b is essentially the same thing. Down here, 2b, the same code, except when I write it out, I write out x, but I also write the value in x. Okay. And you get the value stored at x. X being a string, by the way. So there is essentially the same as the one up above, but it lists out the actual contents, and you can see there's the actual value stored at the array. All right, let's move on to the third test down here. And the third test is, let me get over here. This one here is a little different. It doesn't show, as this one up here had showed us the actual global array reference. This is just going to show us the indices. It's almost the same thing, but it's a little different. Okay, in test 3 again, we start off with the initiator. I should mention that $query will give you the empty string when it runs out of database, or it sees the name of the global array change. Now in my database, I only have up arrow A in it. There's nothing else at the moment. So it runs out of everything. Had there been a global array up arrow B, alphabetically the next global array name, it would have returned the empty string when it ran out of global array A. It would not have gone into global array B. All right, over here we do the query. This is forever do. This is my break here. It's non-standard. Instead of putting quits up here on this line to quit the 4, I have a break which short circuits 4s. Other versions of mumps don't, but I didn't need to do it here. I could have tested for the empty string up there. I could have quit here and gone up and had a test. I find that awkward, but nonetheless. All right, so we get this is the first time through. Of course, we get the first value of the very first index, which of course is up arrow A sub 1. If we get an empty string, we break, which kills the entire loop. Now we get Q length. What Q length does is it tells us how many subscripts there are, how many subscripts there are in @X. For each of those subscripts, for 1 by 1 to whatever I is, we write out a blank, and we write out the subscript itself. So $Q subscript, when you pass it a global array reference and a number, it returns to you that global array index itself, evaluated, by the way. In test 3 there, what we see is the first one there is, and then after we've gone through all of those, after we've gone through all of the global array indices, first time through it's only 1, of course, we will then come down here and we write out the contents of the global array. So the first time through, there's only 1 index, that's 1, and so I immediately write out the contents. Second time through, it's 1, 1, basically, and you see there is I don't know why I put a blank at the beginning, but anyway, I did. This blank here is kind of superfluous, but it's there, you can see it. So I write out the 2 global array subscripts. In other words, this loop right here cycles twice. This loop here cycles twice because the value of I will be 2, and it gets the first index, the second index. And it cycles, then it cycles down to the 3-level index, and so forth and so on. So it gives you a slightly different flavor of how how this works. I should say that using query is probably the easiest way to transverse a tree, or to go through a tree. Technically, of course, you could use order and $data and call a function that's recursive, which is a much more traditional way of doing it in a standard programming language. That's kind of not necessary, because $query is going to present them to you in order through the database. And you can reverse it too, by the way. So it's usually probably enough, although it's possible to do a standard recursive traversal of the database if you really want to. I don't know why you would. But nonetheless, we go to test number 4 here. In test number 4, the purpose is to give us more of the indenting. If I look over here at the beginning here, the first one, I see all this nice, pretty printed indenting. This one down here, test number 4, duplicates it. It looks pretty much the same, as you can see on the scroll. So it's essentially doing the same thing, but it's using query, it's using Q subscript, Q length. It's using more of these functions. The first time I did it, seeing as how I knew the structure of the tree, I could write the code so that it would indent. I knew it was a 3-level tree and so forth and so on. This code here is much more flexible. It does not know how deep the tree is. The tree could be deeper and it'll still work. So that's the advantage of using $query. is that it doesn't care how deep the tree is. It will give you them in order, and then if you just cycle through them, knowing these, because you can find out how many subscripts came back, you can get the value of the subscripts. You can you're on the way. So we start off again with the up arrow A. Now this one here, we copy the value of x into y just before we alter x. We call $query. We get the next value in the database and we store it as x, but the previous value y is there, which you'll see in a moment. If we run out of text, we break. Again, that's my a different way of doing it, but you could use a more standard way if you wanted to. We get the length of what came back. We get the length of the global array reference that was returned, and now we go from 1 to that length, 1, 2, 3. I will be either 1, 2, or 3 in this particular case, because that's 3 is the maximum depth. But we then go and we ask the question whether the Q subscript of y, remember y is a copy of what preceded, is equal to the same position in x. In other words, what I'm doing is, if that's the case, I tab out to j minus 1 times 5 positions. So if j is 1, I don't really tab at all. I just write it blank. If j is 2, I tab out to the 5th position. There's my indenting here. When I indent by no indentation, indentation of 5, indentation of 10 over here. So that's how I'm doing it. If the indices of y, the predecessor, and x, the current, are the same, I don't print anything but a blank. It's only when they differ. It's only when they differ. See the else? Notice the 2 blanks again. That I print out the value of the subscript. So you can see in these cases here, all the way going up and down here, the value of the first index was the same. It was 1. Now for these two here, the value of the second index was the same. It was 1. For these two here, the value of the second index was 2. It's the same. So you don't get anything printed. It's only when the value at that position, that index position, differs from what you had before, that you're going to write out the value. So it gives you this pretty print, which duplicates the one from above. And the one up above, of course, was that way because I knew the structure of the tree. This code down here doesn't know the structure of the tree. This tree could be 7 levels deep and it would still work. It would look somewhat like this. It would indent properly. So it's a little more general purpose than the other one was. And so we write it out. So the purpose is, and after we've done all that, we actually write out the contents, as you can see. Finally, the last one down here is an extension in my version of mumps. It doesn't, as far as I know, exist in others. I didn't write out I guess I did write everything out. My version of mumps does have this additional option for the argument to a 4. Since it is so common to cycle through all of the values of an index in using $order, why bother to go initialize it and have separate lines and have a separate line to test if you got it blank? We know what's going to happen here. So as long as that function is returning non-blank, non-empty string values, the loop will cycle. And it will start at the first one. There's actually a modification of this that lets you start someplace else than at the first. But you can, this is just a shorthand notation for what we were doing up above here. In the very first one here, we see where I said I is equal to empty, and then then was the quit and all that stuff. So all of this structure here is basically incorporated in that in this single figure right here. So you can use it if you want, if you're using mine. If you're not using mine, you probably can't use it. But if you look in some of my code, I use it all the time, and that's all it means. It's just more compact. But you can see over here, test 5 gives you essentially the same stuff. Well, it gives you exactly the same stuff, but it's a little tighter, I think. Anyway, it's not so general purpose. If you want to be totally general purpose, you're going to have to use query, length, and subscript. But this, if you do know the tree, of course, you can do it this way. If you really want to do it recursive, it's possible that if you find if something has a descendant, you can call a function, and that function can can call itself for further levels of depth and so forth, but it's probably not necessary in most cases.